Ultrasound is not perfect always. It struggles to image bones or air-filled spaces like the lungs. The gel reduces friction, allowing the probe to glide easily over the skin. We are mostly interested in reflection. Now, here is where things get really cool. Hey everyone, welcome back to Inside Viewing. Today we are going to dive into the fascinating world of ultrasound technology. From diagnosing medical conditions to guiding minimally invasive procedures, ultrasound has revolutionized the field of medicine. But have you ever wondered how this incredible tool actually works? What's the science behind those images of babies in the womb or blood flowing through your veins? Stick around, because I am about to break down the physics of ultrasound in a way that's easy to understand. Let's get started. What exactly is ultrasound? Ultrasound is a type of sound wave, but it's not the kind you can hear. Human ears can detect sounds between 20 Hz to 20,000 Hz. Ultrasound uses frequencies way above that range. That's millions of cycles per second. These high-frequency sound waves are perfect for medical imaging because they can travel through soft tissues in the body and bounce back, creating detailed images without any harmful radiation. To understand how ultrasound works, we need to revisit some basic physics. Sound waves are mechanical waves, meaning they need a medium like air, water, or tissue to travel through. When a sound wave hits an object, it can do one of three things: reflect, refract, and absorb. In ultrasound imaging, we are mostly interested in reflection. When sound waves hit different tissues in the body, they bounce back at different speeds and intensities. The ultrasound machine uses these echoes to create an image. Now, here is where things get really cool. The key to generating and detecting ultrasound waves lies in something called the piezoelectric effect. Inside this probe are special crystals, usually made of materials like quartz or ceramic like PZT. When an electric current is applied to these crystals, they vibrate and produce sound waves. Conversely, when sound waves hit the crystals, they generate an electric signal. This two-way process is what allows the probe to both send and receive ultrasound waves. There are different types of ultrasound transducers or probe usually used for different purposes, like convex probe, which is used for abdomen, obstetrical, or gynecological imaging. Linear probes are used for superficial structures like thyroid, breast, and vascular imaging. Phased array probes are used for cardiac imaging. Endocavitary probes are used for internal examinations, especially in obstetrics and gynecology. And 3D 4D probes are used to create 3D and 4D images of fetal structures and internal organs. Let's break down how an ultrasound image is created step by step. The probe sends out a pulse of high-frequency sound waves into the body. These waves travel through soft tissues until they hit a boundary between two different types of tissue, like muscle and bone or blood and vessel walls. At each boundary, some of the sound waves reflect back to the probe, while others continue deeper into the body. The probe detects the returning echoes and measures two things: the time it takes for the echo to return, which tells us how deep the tissue is. Second, the intensity of the echo, which tells us how dense the tissue is. By processing thousands of these echoes, the ultrasound machine builds a real-time image of what's happening inside your body. Now, not all ultrasound images are created equal. The quality of the image depends on the frequency of the sound waves. Higher frequencies provide better resolution, meaning you can see finer details. But there is a catch. Higher frequencies don't penetrate as deeply into the body. For example, if you are imaging a baby in the womb, you might use a lower frequency, around 2 to 5 MHz, to see deeper into the abdomen. But if you are looking at something shallow, like a tendon in your wrist, you'd use a higher frequency, around 10 to 18 MHz, for a clearer picture. Now let's talk about a special type of ultrasound called Doppler ultrasound. This is used to see moving objects like blood flowing through a vessel. It works based on the Doppler effect, the same phenomenon that makes a siren sound higher pitched as it approaches you and lower pitched as it moves away. In Doppler ultrasound, the machine measures the change in frequency of the sound waves as they bounce off moving blood cells. This allows doctors to calculate the speed and direction of blood flow, which is crucial for diagnosing conditions like blocked arteries or heart defects. Doctors usually use a gel on the area before performing ultrasound procedure. In ultrasound imaging, gel is essential because it acts as a coupling medium between ultrasound probe and the patient's skin. Air is poor conductor of sound waves, and without gel, air gaps would block the transmission of sound waves, leading to poor image quality. The gel eliminates these gaps, ensuring efficient transmission of sound waves into the body and back to the probe. This results in clear, accurate images and a smoother, more comfortable examination for the patient. Additionally, the gel reduces friction, allowing the probe to glide easily over the skin. In short, ultrasound gel is a simple but crucial component for effective and high-quality imaging. So how is ultrasound used in medicine? The applications are endless. Here are just a few examples. To monitor development of a fetus during pregnancy, to assess heart functions and blood flow, to diagnose the injuries in muscles, tendons, and joints, to quickly detect internal bleeding or organ damage. But ultrasound is not perfect always. It struggles to image bones or air-filled spaces like the lungs, because sound waves don't travel well through these materials. That's why other imaging techniques like MRI or CT scans are sometimes needed. But for many applications, ultrasound is the best choice because it is fast, portable, and cost-effective. And there you have it, the physics behind ultrasound technology, from sound waves and piezoelectric crystals to real-time imaging. It is a perfect blend of science and engineering that revolutionized the medicine. If you enjoyed this video, don't forget to give a thumbs up and share it with someone who loves science and healthcare. Don't forget to subscribe and press the bell icon so you don't miss out more mind-blowing contents. Thanks for watching. I will see you in the next video.